Let's consider a gas that is inside a cylinder. Um, so we have a gas inside a cylinder. The cylinder has cross-sectional area A. So if I look at the area here, area A, and the total volume then is going to be volume V is A times S. And if you consider the mean pressure exerted by this gas, there is a force, a mean force that is exerted by the gas molecules, F bar, and therefore the mean pressure exerted by the gas molecules on the right hand side here is equal to F bar divided by A. So that is the mean pressure, and F bar is the mean force due to the gas molecules. And on this side of the cylinder I have basically a movable piston. So this is a movable piston. So if the piston is moved very slowly by an amount ds, there will be a change in the volume of the gas. Okay, so let's say that the piston is moved very slowly by an amount, so there is a total displacement ds, so that there will be a change in the volume of the cylinder that contains the gas. It will be equal to area A times ds. So this will be the new location of the piston. So when I move it by a total amount ds. So what is the work done on this gas in the fluid? Well, the work done, it's infinitesimal work done on the gas is equal to the minus work done by the gas. So minus, since we have a pressure, mean pressure P multiplied by A gives us the mean force. So mean force is P bar times A multiplied by the displacement it causes ds. Since this is the pressure exerted by the gas, the work done by the gas will be F bar times ds. Work done on the gas will be minus F bar times ds. So this will be equal to minus P bar A ds, and A ds is the change in the volume. So I will find that the infinitesimal amount of work done on the gas is minus P bar dV. So when we do this in a quasi-static process very slowly, the infinitesimal amount of work that we do is minus P dV. Then if I continue with this from an initial volume to a final volume, I have to integrate from initial volume to final volume P dV, or integrate from final volume to initial volume mean pressure dV. So this is the work done on the gas inside the cylinder when we change its volume. You can see that the work done on the gas is going to be positive only if delta V is negative. So if delta V is negative, minus minus will become plus. That means the final volume minus the initial volume should be negative, or the final volume should be less than the initial volume. That means the gas is compressed. So the work done on a gas is only positive if the gas is compressed. And similarly, work done is going to be negative if V final is greater than V initial. If delta V is positive, that means the gas expands. So this implies that the gas is doing work. The work done on the gas is negative. So in the quasi-static process, where we're not disturbing the equilibrium at all times, the pressure of the system, mean pressure, and volume are going to be well defined. So we can represent the process in a P bar V diagram, as you can see here. And this is happening because the system is kept approximately at equilibrium at all times. So looking at this PV diagram going from V initial to V final, you can see that here I have V final less than V initial. That means the gas is compressed, compression, and the work done is going to be positive. So the work done will be given by the area under this curve. So this is the work done on the gas. It's going to be positive. And you can see that if you look at the sense of the process, if the process is proceeding from right to left using the right hand rule, you can see that if you curl your fingers in the direction of the process, your thumb points up, so you have a counterclockwise sense is going to give you a positive work, so the area will be equal to the work. If it's a clockwise sense, then you would see that your right hand rule would give you the thumb pointing into the page, which will imply that the work is going to be the work done on the gas is going to be negative. So only in the case where we have a compression, when the final volume is less than the initial volume, the work done on the gas is positive, and it gives us the counterclockwise sense using the right hand rule. You can see that your thumb points up towards you. That means it's a positive work we're doing. If the thumb points into the page using the right hand rule, when you curl your fingers in the direction of the flow of the process, you will see that the work done on the gas is negative. The gas is expanding. So in the quasi-static process, once again, we're doing the process very slowly. We're keeping the equilibrium at all times. If you have a gas inside a cylinder with volume A times S, with a movable piston on one side, the mean pressure exerted by the gas on this movable piston is the mean force per area. So its mean force is mean pressure times area. If the movable piston moves by an amount ds, the work done by this force will be F times ds, that is work done by the gas, but work done on the gas is minus F times ds, so minus P bar A ds. So the work done is minus P bar dV for infinitesimal amount of work done. And therefore we find that macroscopic work done from initial to final volume is minus the integral P bar dV, which tells us that if the volume is decreasing, delta V is negative, work done on the gas is positive, the gas is compressed. If delta V is positive, the gas is expanding, work done on the gas is negative. And P bar and V are equilibrium values throughout the process. So this is at equilibrium at all times. And therefore you can represent such a quasi-static process in a PV diagram where you see, so we have a P bar V diagram. You can see that the area enclosed by the curve from initial to final point gives you the work done. If the flow of the process is in the counterclockwise sense, if it's in the clockwise sense, then the work is going to be negative. So the area with a minus sign will give you the work done on the gas.